Imagine a black hole as a space-time event, a region where the internal gravity is so intense that the rules of reality effectively dismantle. For decades, we could only theorize about these regions because they emit and reflect zero light, making them impossible to see against the black of space. The Event Horizon Telescope collaboration solved this by ignoring the black hole and measuring the radio waves from the superheated gas swirling around it. These scientific plots represent our first empirical proof of the object's presence. That data translates into these asymmetric rings, revealing the physical boundary of the black hole's shadow and the shape of the trap it sets. There is an inherent irony here. We can never observe the object itself, only the glowing silhouette of the vacancy it leaves behind. That silhouette is formed by the accretion disk, a storm of gas and matter spinning so fast it reaches temperatures in the billions of degrees. As matter approaches the center, the gravity becomes so strong it warps the fabric of space, forcing light to follow a distorted path in a process called gravitational lensing. Light leaving the back of the accretion disk is pulled 90 degrees by the gravitational field, arching right over the top and bottom of the black circle to form a halo. This creates an uneven ring. Due to Doppler beaming, the side of the disk spinning toward us appears brighter and bluer, while the receding side fades into a dimmer red. Closer to the edge, in the photon sphere, gravity is so high that light actually orbits the black hole multiple times before it manages to escape and reach your eyes. Because light always follows the shortest possible path through the universe, these curves reveal the literal geometry of the environment. Near a black hole, space and time are no longer straight lines. To see what happens next, we have to split the narrative into two viewpoints: a safe observer in the distance and an infaller dropping toward the center. From the safety of the distance, the observer watches the infaller approach the dark threshold. Albert Einstein's theory of gravity tells us that mass warps the flow of time. At this distance, that effect becomes visible. The light waves reflecting off the infaller stretch out, causing their image to turn deep red and fade. To the observer, the infaller's clock appears to slow down so dramatically that they eventually seem to freeze at the very edge of the boundary. No matter how long the observer waits, they will never see the infaller actually cross the line. The observer pays for their safety with a permanent loss of data. They are mathematically barred from witnessing the infaller's true fate. Now we shift to the infaller, who experiences this descent in real time. They have reached the Schwarzschild's radius, the exact distance where the boundary forms, determined entirely by the black hole's mass. Crossing this radius means entering the event horizon. Inside this sphere, the speed to escape exceeds the speed of light. Paradoxically, if this is a supermassive black hole, the curve of space at this distance is relatively gentle. The infaller wouldn't even notice the moment they pass the threshold. They enjoy a smooth, undetectable crossing, only to find they have passed a one-way gatekeeper with no path back to the universe they left. Once inside the horizon, there is no stopping. The infaller is pulled toward the center, where the gravity begins to work as a deconstruction tool. They are now subject to tidal forces. The pull increases so rapidly that the force acting on the infaller's feet is millions of times stronger than the pull on their head. This starts the process of spaghettification. The infaller is violently stretched into a long, thin line and compressed from the sides. The vertical tension becomes so high it overcomes the forces holding matter together, ripping apart molecular and atomic bonds. At this depth, the physical cost of gravity is the complete and irreversible destruction of atomic cohesion. The remains of that infaller are now a stream of subatomic plasma falling toward the exact center of the space-time event. This is the singularity. General relativity predicts that all the mass falling into the black hole is crushed into this single point of infinite density. But at infinite density, our mathematical models fail. The clash between our understanding of the very large and the very small means our equations stop making sense. The existence of the singularity forces a compromise in astrophysics. To map the universe, we have to account for a place where every mathematical law we know ceases to function. A black hole presents two versions of reality. One is a quiet, frozen fade for the observer, and the other is a violent deconstruction for the infaller. The event horizon acts as a permanent quarantine. shielding the rest of the universe from the broken physics that exists behind it. Once matter moves toward that singularity, there are no alternate routes and no escape trajectories, because at the very center of a black hole, time and space as we understand them simply cease to exist.